Welcome everyone to this seminar about failure and crack propagation and failure modeling in Marc. This is a picture of me. So this presentation is divided into two parts. I will talk about two aspects of failure modeling. One is material degradation, which in its simplest or the most common case, I would say, we can have plasticity. Sorry, I will not talk about that today. We can also have things like progressive failure analysis, which is often used in composites, and also damage mechanics for metal damage typically, which is something I will bring up later in this presentation. The second part is about structural failure, where we have material separation. Essentially, the parts break up. And here the talk will be about interface delamination, interface between materials typically. Initiation and propagation of cracks will also be discussed in the seminar. So I will start with some three basic questions you may ask yourself in failure analysis. And the first question would be, where does the structure fail? And to answer that, you typically use a failure criterion of some kind, where stress could equal some sort of maximum stress, like a yield stress or a breaking stress of some sort. You can have a failure index, like used in composites, for instance. You can have a critical damage strain, which marks the onset of failure. Or in fracture mechanics, you have some sort of fracture mechanics criterion, like the energy release rate reaches a critical value. Secondly, you may be interested in where it fails. And typically, of course, if you have a failure criterion, your structure would fail at the location of the maximum, the failure criterion, or where the failure criterion is fulfilled. So that's what would be the place. You can also specify upfront by giving an initial crack. And by doing so, you would specify where the structure would fail. The third question, which is the topic of this seminar really, is what happens after you get the initial failure. You indicated a failure somewhere, you know where it is, and what do you do next? Three things we can do using the tools in Marc. We can do a progressive failure analysis. We can do a damage evolution calculation. Or if it's a crack, we can do propagation of that crack. And the two last ones are the ones which will be the focus of this presentation. Just a couple of words about progressive failure analysis, which in the formulation we use in Marc is based upon a linear elastic material, typically orthotropic, where the stiffness is changed when we get failure. It's often used in composites, and the models we have in Marc for the failure index, some of them are listed here, Pak, Saivu, Hashin, Hill. We have a few more as well, and we have some models for describing how this material stiffness is decreased due to the failure. Switching over to the damage mechanics, we have a number of material models in Marc for that. Since many years, we have the Gerson model, the Lemaitre model, a principal stress in Noyan. The Lemaitre principal stress and Noyan are more post-processing type of damage models. They don't change the material stiffness. You may deactivate elements when a failure criterion is fulfilled there, but otherwise they don't influence the analysis. In the upcoming release, we have added a model by Professor Bonora for metal damage. I will talk more about that one. And we also have some rubber damage models used for rubber material models. The Bonora model, it's based upon modeling generation, growth, and coalescence of voids, similar to the Gerson model that we already have. It has some special formulations. It's a pretty new model. It's been around for a few years, but we have implemented it for this upcoming release. The damage evolution and the plasticity evolution, it always works together with plasticity, but the evolution equations are separate for the damage and the plasticity. One special thing with it is that the Young's modulus is varied with damage, which is one of key features of this model. Another key feature, another important property, I should say, is that the material parameters are easy to determine, straightforward, which of course is very important when you need to determine them. One important aspect of this is that it has a so-called non-softening formulation with the varying Young's modulus. So it has not problems with mesh size dependency that some material damage models have. And that's a very important one, because you don't need to have special formulation like to deal with mesh size dependency of the damage. The input parameters consist of 4 quantities: the threshold plastic strain when damage starts, and the strain at failure, and the critical damage at failure, and there's an exponent that needs to be determined for the evolution equations. The damage variable can be related to the Young's modulus, with the original Young's modulus E0 and the current one E. So the damage variable will be 0 for a non-damage and goes up to 1 as usual with these type of models. And of course, the damage variable itself has an evolution equation, which is the core of the model, of course. Here's an example where we have a crack which is initiated and it's growing by means of the damage model. So you start out with a surface crack and it grows, and the purpose of this exercise, from what I understand from the one I got it from, is that they want to try to determine the fracture mechanics quantities based upon this damage model. And they combine it here with element deactivation when a certain damage level is reached, so you can expand the crack. And this brings me to the second part of the talk, the material separation, where it breaks. And it's divided into 3 parts, where we look at failure at interfaces, interface between materials or some other sort of interface, where we will deal with the breaking glue option and the delamination option in Marc. Crack initiation is a new feature that we have in the latest release, where you can specify that inside Marc a crack will be initiated, so you don't have to create it during pre-processing. We have 2 options there, and we'll mention them further in the presentation. And finally, the crack propagation. Since many releases, we can do growth along glued contact interfaces. That was up to now the only option for 3D, full 3D. Now we can also grow along element faces and element edges for 2D and shells. And previously we could do general directions with remeshing in 2D and shells, but now we can also do that for 3D solids with tetrahedral elements. Starting out with the breaking glue option, I will use this structure with a T-section glued to a plate, which in turn is glued to a rigid body, just to illustrate the various models. So the green part here is just a rigid body, which I use to pull this thing upwards, so we get some damage below here. So in the glued contact, we glued these parts together, and we define a failure criterion in terms of the contact stresses, the contact normal stress, contact tangential stress, and some material parameters. And when this criterion is fulfilled, everywhere where it's fulfilled, we change the glued contact into regular contact with friction and sliding, etc. So we thereby model the failure. And if we take this example and I take out part of the model so we see what's happening below it, We see in yellow the region which has been released from glued and it's just doing regular contact. In this case, it's just pulling, so it's just separating. And we can model this failure. However, this option is useful in many cases, but often you want a more detailed description of what is happening in the interface. You're not happy enough with just using these stresses like this. And for doing that, we have offered two models in Marc, the cohesive zone model and fracture mechanics with crack propagation. So in the cohesive zone model, we put a layer of interface elements between the parts where we suspect we will get failure. And we use a special material model for this interface, the cohesive zone material model. This interface is plastic initially until it breaks, and it may or may not impact your stiffness of the structure. In the fracture mechanics approach, we propagate the crack along this interface. In previous releases, we were only able to do that if we glued them together. Now we can use shared nodes. We divide them into two parts, and we say along this interface, we have a crack, and we can grow it. But we need an existing crack. You have to set the crack before, so unless you do something else, you will have to put it there. So the cohesive zone model, the material model, it describes the traction versus the opening displacement, so how much the thickness increases of the interface elements in principle. So the stress versus displacement. Initially, it's elastic, this portion. And then at the critical opening displacement with a corresponding critical stress, it will fail. It will not fail abruptly because it still has some stiffness. So as the element opens up, the resistance will be less until some negligible value. And the failure criterion for this, when you have this type of element, is that you reach the critical opening displacement, or in other words, you reach the critical stress in the interface elements. So how do we have them? Well, in the pre-process, you create a mesh with interface elements. There are good tools and that for this, so you can just say, split it up here and insert the elements and figure out what's top and what's bottom and just connect it, and then you can run it. The flip side is you need to put this everywhere. You may get a failure, which may or may not be a problem. If we have cracks, fracture mechanics, yeah, we add the cracks during the pre-processing, or you can add them in Marc, and that will be shown later in the presentation, but you have to add them. What if we want to do this automatically? Yes, we can, and to do that, we use the so-called delamination option, which is not only related to delamination in composites, but it's general delamination between parts, regions. So in that, you have the toolbox, your cracks, your initiators, your delamination, and you can define a delamination at a material interface, which is typically what we use here. So what does it do? Well, it answers the questions, if you like. When does it fail? We have the failure criterion, similar or more or less exactly like the breaking glue. You have the normal stress, you have the tangential stress. It's a normal stress in the system defined by the interface. So we have material 1, material 2 typically. You have the stress in between. It only breaks, of course, in tension, so the equation is not complete, but in principle, this is what we do. Where does it fail? Well, wherever this failure criterion is larger than 1. So where the failure criterion is fulfilled, it will fail, it will break. There is actually a new option now where you can say only fail at a single node where it is maximum. So with this, where it's larger than 1 could be a large region, could be much larger than shown here, but it will only fail at 1 point. But normally you would say everywhere where it's larger than 1, just let it fail there. And here we have reached 0.81859, so it's about to fail in the middle. Then comes the interesting part. What do we do when it has failed? Well, what it does, it breaks up the mesh. Initially, there was no double nodes or anything where this failure occurred. So we break up the mesh, and after that, we have the option to activate the VCCT. So this shows the crack tip system of the crack that we added. Or you insert your interface elements. And those are inserted where we break up the mesh, where we would otherwise get a void in the model. So we fill that void with the interface elements, and then they are active and take part in the analysis. If we use VCCT, and code automatically adds as many crack fronts as you need. In this case, it was one crack. It was a circle crack in the middle, as you see there. Together with that, you use a template crack, which defines the properties of the crack, or the VCCT definition, I should say. If you have growth, the growth criterion. In this case, I just say that the total G should be larger than the crack growth resistance. I could choose any of the other crack growth criteria available in Marc for mixed modes, etc. Here I just took the simplest one. You also define in the template crack how it should grow, and here I say stay on this material interface and grow along element faces, and this is what it does. So as the load increases, the crack grows more and more. Next, if we activate interface elements, this movie illustrates that. You start out with element type 7, the pink one, which is the standard brick element in Marc. When we get failure after a few increments, it inserts element 188, which is the corresponding interface elements. And we see here in the middle, they disappear, and that's why I added a feature to deactivate the interface element when it has reached full failure, when it's completely failed. So it doesn't contribute to the analysis, so we just take it out. And to sum up what we're doing here, when we use this option, we use the stress criterion to determine the initial failure. If we switch to VCCT, then we use the fraction mechanics to decide if it should grow further. And when we do that, we typically turn off the stress criterion because we don't want to have two potentially competing criteria. So we want the crack properties to determine if it should grow, and not a stress at a crack front where the stresses are kind of meaningless because they're very high due to the stress angularity. So you typically turn it off. If you use cohesive, you let the stress criterion continue to determine if it should grow further. Here we don't have the singular stress thanks to the inclusion of the cohesive zone, the interface elements. And if we recall the material model, the standard model, you have an elastic portion up to the failure, and then you have a decline in stiffness. What we do here essentially is that we skip the elastic part of the cohesive elements. So they are initially stiff, if you like. Well, they don't even exist. It's a perfect bond at the interface. So we skip the elastic part. When we insert them, they immediately start to fail. So we don't have any non-failing cohesive elements in there. If we compare the VCCT and cohesive, it's kind of similar. Incidentally, you can see we have the GC, the crack growth resistance, corresponding to a fracture toughness. We also have the same variable name here, or the name of the material parameter, and they are related, but they're not the same thing. It's not the same thing to use VCCT as to use cohesive, because they behave differently. I mean, for VCCT, once it grows, you have a free surface. There is no tension at all in that surface, the crack surface. If you have cohesive, they hang on for a while, and only when they have lost all the stiffness does this tension disappear. So you shouldn't expect the same results using the same GC for VCCT as in cohesive, but they should be similar. It's not the same thing. Okay. moving on to the next part of the presentation and the initiation of cracks. We introduced the option now to insert a crack inside Marc in the analysis. Previously, normally you just create your crack in the preprocessor and run the job with that crack. Now you also have the option to do that inside Marc, and you can add the crack at the start of the analysis. You can do it to start at the load case. You can preload without a crack and then add it. But you, as a user, decide where the crack should be. And in order to do that, we introduced the concept of a so-called crack initiator. And that crack initiator can come in different flavors. One is that you specify a set of element phases which are present in the model. Sometimes convenient to just say I know exactly where the crack is and it's along the element phases I have in the model. So I just select that set and say this is where my crack should be. Or you can use a general faceted surface and you use remeshing. Like in this case, you have a circular disc, creates a surface crack. Here's a through crack. You will create two crack fronts, one there and there. And after you remesh, you have your cracks in your model. So here's an example of my favorite example here. I define here as blue is my selected element phases. I actually selected a somewhat too large area here. Some of these are on surface, but it doesn't matter because Marc only uses the element phases we are actually internal to the structure. And at that point, it creates the cracks needed, it splits up the mesh. And in this case, we get two straight crack fronts because of the shape of this selected area. And just as with the delamination option, you combine this with a crack template, a VCCT crack template, where you say if this should grow, how it should grow, when it should grow, etc. So if I use the same settings here as I used in the delamination example, we will see the crack is growing. It starts out with two straight fronts. It grows for a while, and fortunately, at the final load here, we get the same crack front as we got with the delamination option, which is very fortunate, of course. The second option, that's where you define your crack as the intersection of this faceted surface and the mesh. So here's another example of that. We inserted during remeshing, and this faceted surface, it's nothing but a meshed surface. You can define it in Mentat. Just take a general, any surface in Mentat, under NURB surface in Mentat, and just mesh it. There are tools in Mentat for doing that. Or you can, if you have it as a CAD model, you can import it through the CAD-Fix interface as a faceted surface. And then you can use it directly. You can position it wherever you want. You can scale it, etc. Just as any other surface in Mentat. And illustrating that on our favorite example here, I just took a circular disc, put it somewhere at the surface, partly inside, partly outside. This is the crack I get. This is just an outline plot showing the crack front, and here are the arrows showing the crack tip system, the local X direction of the system, to see where it is. And we see here we start out with the hexahedral elements mesh, just because it was easiest to create. And the remeshing here is based upon lower order tetrahedrals. And here we also use a new feature of the new release of Marc, where we have a good control of the mesh density. I can just say that when we're close to a crack front, use a certain edge length of the elements, and you can use a larger edge length outside, so you get transition in mesh density. That's very important when we deal with cracks, because otherwise you would have to have a very fine mesh in your model, but here you can have a focused mesh where you need it. This brings me to the final part of the presentation, which is about the new features for crack propagation. We have already seen examples where we grow along element faces, and here show some examples of growth along in general directions, I should say, arbitrary directions with remeshing. So we use lower order tetrahedral elements that we use in the measure, remeshing. We use the new adaptive TET measure that we're also introducing in this release, which allows the finer measure on the crack front. And whenever there is growth of a crack, we expand the crack surface, and we remesh using that expanded surface and split it up so that we get an expanded crack. So the first example here is a solid cylinder. I pull it a little and then I twist it, and then at equal intervals I let the crack grow with a predefined increment. And you see that you get a nicely focused mesh around the crack front, and you get coarsening where you don't need any fine mesh anymore, and you get this twist of the crack front as expected due to this loading. Here's an outline plot of the same analysis where you see the estimated growth directions for each crack front load. So it starts out straight. I used the crack initiator, which was straight, and then the front twists with the analysis. And then finally, I have another example. It's a pipe, a thick-walled pipe with a crack, which is partly through the thickness. Here's my rectangular crack initiator. It goes through something like half the thickness. So that's where the crack starts. I just pull it, constant tension, and then have a constant growth increment every 0.1 second or something like that. And I just let it run and see what happens. It starts out as a crack initiator, and it slowly but steadily grows through the whole section, almost through. And similarly, this outline plot, you see it starts out as a single crack. It hits the internal, the inner part of the cylinder, which is then treated as a boundary, of course. It splits up the front into two fronts. It goes around, and it almost makes it at the end. I would have to have a much higher mesh density to be able to resolve what is happening at the end. It's a challenging situation to get it to grow all the way through. And that concludes my presentation. Half an hour has gone, and I'll leave it open for questions.